My name is Mario Grando. I'm an electrical engineer for the Pacific Northwest National Laboratory. Today, I'm presenting at the IEEE Sensors 2020 conference as an author and also as a member of the Project 8 collaboration. I will be giving a talk on a microwave sensor array for next generation neutrino mass measurements. The purpose of this presentation is to outline the progress on the design of a microwave sensor array to measure neutrino mass. In this presentation, I will cover an overview of the Project 8 collaboration, the configuration of Phase 3 experiment, our most recent work, our approach to defining requirements for the sensor array, and a proposed array design. Project 8 is an international collaboration whose goal is to measure neutrino mass using a technique called cyclotron radiation emission spectroscopy, or CRESS for short. This technique uses tritium. Seen in the upper right-hand illustration, the radioactive beta decay of tritium will result in a helium particle, an electron, and an antineutrino. The electron's kinetic energy resulting from this process will vary. The probability of these kinetic energy levels occurring is represented as the electron energy spectrum, pictured for tritium on the right. The maximum possible electron energy, around 18 kiloelectron volts for tritium, is referred to as the spectrum endpoint. The CRESS technique places a tritium gas source into a large external DC magnetic field. When the electrons from the resulting beta decay encounter this external magnetic field, they will undergo cyclotron motion. The cyclotron motion of an electron generates an electric field that can be directly measured. The frequency of this electric field is a function of the electron's kinetic energy, its mass, and the applied DC magnetic field. These detected electron kinetic energies over many beta decay events will trace out the energy spectrum for tritium. Because this is a statistical process, experiment sensitivity scales with the number of events. The presence of a detected neutrino mass would result in reduced electron endpoint energy and would distort the shape of the electron energy spectrum endpoint, as seen in the inset image example. From this distortion, the neutrino mass can be inferred. The Project 8 effort is organized into 4 distinct phases. Phase 1 was a proof of concept stage using a waveguide detector and krypton gas as the source. Phase 2 was a waveguide detector that used both krypton gas and molecular tritium as a source. Phase 3, the subject of this presentation, will implement a free space phased array beamforming detector. This approach also uses molecular tritium. The sensitivity to neutrino mass for this experiment is expected to be around 2 electron volts. Phase 4 will scale up in volume, uses atomic tritium, and will realize the Project 8 goal of establishing an upper bounds of 40 millielectron volts to the mass of a neutrino. The picture on the right is a spectrogram of a single electron radiation event measured in Phase 1. The broken lines are the cyclotron radiation emissions from an electron. The reason these lines are not continuous are due to collisions of the electron with particles in the gas. Below this image is a waveguide detector comparable to the Phase 1 and Phase 2 detectors. The Phase 3 experiment will have a volume of approximately 200 cubic centimeters. For the given experimental parameters, a single electron event is expected to yield only around 1 femtowatt of radiated power at 26 gigahertz. The conceptual drawing of the Phase 3 experiment to the right shows some of the critical design features. The molecular tritium, which will be housed in an RF transparent gas cell at the center of the experiment, is shown in purple. This cell will constrain the gas within the detector volume. The gas cell is then surrounded by a cylindrical array of antennas, here shown as microstrip patch antennas. The antenna array is a radio collection of passive linear subarrays. These subarrays will be digitally beamformed in post-processing to steer through the gas volume in search of trapped electrons. Magnetic field trapping coils, used to trap electrons in the tritium gas cell region, are shown in green. All these items will be cryogenically cooled and placed into the bore of a large 1 Tesla MRI magnet pictured in the lower right. To successfully register an electron event, the sensor array must detect electrons above the background instrument noise levels. For initial SNR requirements, we considered the following simple model. A stationary electron is centered in the detector volume. It is assumed the antenna arrays are equally distributed in a circle around the stationary electron, as seen in the image at the bottom. Free's transmission formula was used to infer the path loss. This calculation was performed from an electron source radiating 1 femtowatt at 26 GHz with a directivity of 1.4 dBi. Each element in the array is assumed to be connected to a low noise amplifier with a noise temperature of 20 K. The figure in this slide shows an example SNR as a function of the detector array radius. The proposed design for the Phase 3 system is an inward-looking cylindrical phased array. Passive subarrays along the longitudinal axis will be phased together to create a beam that can be scanned along the polar axis to desired locations within the gas cell. This beamforming is accomplished digitally during post-processing, as data from each subarray will be recorded during the experiment. A Python-based beamforming code was developed to explore beam shape and side lobe levels for different steer locations within the gas cell. This code is developed because other higher fidelity simulations took many hours to compute. Using the beamforming code, different phasing and amplitude tapers can be quickly explored. To the right, we can see different steering locations around the polar axis of the gas cell. Above is a finite element simulation that shows good agreement with the beamforming code. In this slide, we are looking down the longitudinal axis of the array using the beamforming code. For this example, on the right, there are 30 channels of passive subarrays. Each subarray consists of 14 elements. Here, we explored the effects of the amplitude tapering and steer locations. As you can see, using a linear amplitude taper, as seen in plot A when centered, and again in plot C when steered to 3 centimeters, provides a much more uniform power in the main beam, but does not cover the entire longitudinal length of the gas cell volume. A uniform taper, however, plots B and D, shows wider coverage of the gas cell volume at the cost of less uniform power in the main beam. The uniform taper is currently the preferred approach because of the wide coverage area in the gas cell. Rings of linear subarrays along the longitudinal axis are currently being investigated to optimize coverage. But this approach must be weighed against costs due to the additional requirement of more channels and thus more hardware to cover the full longitudinal axis of the gas cell. Requirements for the array were then determined. A pattern must be broad, and given the electron's vertical polarization, must also be vertically polarized to match. The array center frequency must be 26 GHz for a 1 Tesla field. To properly steer through the volume without grading lobes, the linear array channels must be spaced within a 1 wavelength element spacing from each other. And so a single subarray must fit those dimensions. To cover the electron energies near the endpoint spectrum, a bandwidth of 10 MHz is required. In addition to these requirements, the arrays must also survive a low temperature vacuum environment in the presence of high magnetic fields. Over the length of this effort, several possible element candidates were considered. 2 approaches were down-selected and heavily modeled. These were the microstrip patch array and the slotted waveguide array. An example of the patch implementation is pictured. Recently, the collaboration has down-selected to the waveguide slot array. The 2 down-selected approaches had multiple advantages and disadvantages. Considerations included cost, complexity, environment, and performance. Ultimately, the waveguide slot array was chosen. This was in part due to losses in the feed structure required for the patch array. As a proof of concept, a 10-element linear waveguide slot array was constructed. As it turns out, WR34 waveguide width is very close to the width required for a 10 centimeter radius, 30-channel detector, which was the leading approach at the time. The slot impedance or location was optimized for a uniform taper. On the upper right hand, we show a polar plot of the expected array patterns. Also, a picture of the array is constructed by PNNL. 4 arrays in total were constructed to demonstrate repeatability. The plots below show measured VISWAR compared to a finite element simulation, as well as the measured far-field patterns also compared to simulation. Shown here is a simulation of a full 30-channel waveguide array. In this simulation, the array channels are composed of 10-element passive linear subarrays. As you can see, much of the cylindrical array surface area is metal. This metal can cause a ringing effect on the beam pattern. Current investigations are showing promise by using absorber to dampen these ringing effects. Side load levels are a concern, but do not have to be drastically reduced due to post-processing efforts and due in part to an expected SNR of 6 dB. In this presentation, we investigated a microwave sensor array for electron detection in the Phase 3 Project 8 experiment. The initial design concept is a cylindrical, inward-looking, near-field focused phased array. Planned work is to fabricate a 30-channel detector consisting of 5-element passive subarrays of slotted waveguides at room temperature. A mock electron source will be used for analysis and validation. It has been determined from simulations that a smaller collection of 30-channel 5-element passive subarrays are more effective. Larger ring diameters with more than 30 channels are also being considered based on performance results from simulations. At this time, I would like to acknowledge our sponsors, the U.S. Department of Energy Office of Nuclear Physics, the U.S. National Science Foundation, the Prisma Plus Cluster of Excellence at the University of Mainz, as well as internal investments from all of our collaborating institutions. To give you some idea of the collaboration effort, here are the names of contributing staff and their institutions. These people across multiple organizations have come together to develop the physics and hardware, the details of which were much abridged in this talk. I highly recommend the Project 8 website, www.project8.org, to see a list of publications related to this experiment. Thank you for taking the time to listen to this presentation.